compliance, which is sometimes called capacitance or distensibility, refers to the ability of a blood vessel to respond to an increase in pressure by distending or swelling and increasing the volume of blood it can hold, or on the flip side, with decreased pressure, a decrease in volume. The way that this applies to blood vessels is to remember that they're stretchable tubes, like rubber hoses, rather than lead pipes. So if the pressure increases, the walls of the tube can actually stretch out a bit to accommodate a larger volume. And exactly how much they stretch out depends on their compliance. Now, we can calculate a given blood vessel's compliance, C, by dividing the volume of blood, V, in milliliters, by the amount of pressure, P, in millimeters of mercury that the blood's experiencing. And so we measure compliance in milliliters over millimeters of mercury. So when we plot out volume as a function of pressure, the slope, or volume over pressure, is the compliance. If you plot for the veins, they have high compliance, meaning they're high volume, low pressure vessels. And even a small increase in pressure expands the volume a lot. The arteries, on the other hand, have low compliance and are low volume, high pressure vessels, meaning with the same amount of pressure, their volume doesn't expand as much. Furthermore, a hardened artery would be even less compliant and is kind of like a lead pipe. In other words, it takes an incredible amount of pressure to change the volume even a tiny bit. With that in mind, since veins are more compliant, the majority of blood in the body at any given time is in the veins, whereas less blood's in the thicker, less compliant arteries at any given time. Now, when the arteries harden due to arteriosclerosis, they become even less compliant over time, which means they can't hold as much blood volume at the same pressure. That volume of blood that it can't hold anymore has to go somewhere, so it ends up in the veins. In this situation, blood simply moves away from the higher pressure arteries to the area of lowest pressure, typically where the compliance is highest, like in the veins. Now, if compliance, or volume over pressure, is its tendency to stretch out with pressure, then its inverse would be its tendency to not stretch out with pressure. Or another way to think about it is its tendency to recoil back to its original shape, which is a concept known as its elastance. Now, both of these concepts are super relevant for large elastic arteries like the aorta, which literally comes right off of the heart. Now, first off, heart cells take ATP and use that chemical energy to contract during systole, turning the chemical energy into mechanical energy. This propels blood out into the aorta. Since it's moving blood, it has kinetic energy. But also, since it's exerting pressure on the walls of the vessel, it also has pressure energy, which is a form of potential energy. And the sum of these two is equal to the total energy E, which we'll represent by this little health bar thing, which is filled with kinetic energy in blue and pressure energy in purple. So let's just say that during this time, that pressure energy corresponds to a pressure in the vessels of 140 millimeters of mercury. After the heart contracts, it relaxes and fills with blood, which is called diastole. Now, during this time, blood's still moving a little bit and there's still pressure, but there's much less total energy. So if there's less pressure energy, then let's say that it corresponds to something like 50 millimeters of mercury. If we take the difference between the systolic and diastolic pressures, 140 minus 50, then we get 90 millimeters of mercury, which is actually called the pulse pressure. Alright, but in reality, even though the aorta is an artery and isn't very compliant, during systole it still stretches out with these high pressure contractions. And some of that volume is held in this distended space. Since the aorta is very elastic, the walls store some of that energy of contraction as elastic energy in the walls, which is another form of potential energy. Since this total energy has to be the same as it was before, that means that there's less pressure energy and kinetic energy to make way for that elastic energy. So less pressure energy means that that blood pressure isn't as high. Let's say around 120 millimeters of mercury instead. Now, during diastole, those highly elastic walls recoil or snap back, which moves that blood that was held during systole out into the circulatory system and releases that stored elastic energy, converting it back to pressure energy and kinetic energy. So now pressure energy gets added during diastole, which let's say yields a higher pressure of 60 millimeters of mercury. This means that the new pulse pressure is actually lower. 120 minus 60 is 60 millimeters of mercury. So with elastic arteries, the blood pressures are 120 over 60, with a difference or pulse pressure of 60 millimeters of mercury. And remember that in the first example without the elastic properties, it was 140 over 50, with a pulse pressure of 90. So here we see that these large elastic arteries, like the aorta, buffer or dampen the pulse pressure. And this whole phenomenon is known as the Windkessel effect. As a person ages, healthy, compliant arteries become stiff and non-compliant. And this results in blood vessels that behave a lot more like the non-elastic case, which means pulse pressure ultimately goes up. Alright, as a quick recap, compliance refers to the volume of blood a vessel can hold at a certain pressure, and this is related to distensibility. Arteries are low volume, high pressure vessels, and therefore have low compliance. And veins are high volume, low pressure vessels, meaning they have high compliance. Aged arteries become much less compliant, which leads to higher blood pressure in the elderly.